So last time I failed to explain in time, so let me do it one by one. So this one, in particular, this B hat community computational B hat and side dagger is given like this. And this one last time I said it right, so I'm not going to repeat the ratio. So this one is nothing B hat side xn. But so multiple things. Just acting a bunch of operation operator on the vacuum, and we want to compute. And of course, so to compute this quantity, so you just do the computation relation. You have to use the computation relation. Okay. So let's do the first step. You commute. Try to commute this first one. And what you get is that the so use this computation ratio side dagger xn and the hat side xn minus 1 dagger here, like this way, and the plus so this quantity. We choose y e y minus x and then side dagger xn and low of y, and then side dagger xn minus 1 side dagger x1. Like this way. Oh, by the way, so every time I try to record the lecture, if you think I forget to record, please remind me. Otherwise, you cannot. Anyway, so recording and so on is just that you can just review or like anyway review what's what's taught in this lecture. So I mean, I try to make you as much as focus on what I try to say as much as you can. So that this note is given, record is given, so you can just focus on what I try to say. So that you can. Sometimes taking notes will distract your attention. So sometimes. Anyway, so all the recording purpose, writing lecture notes or sharing of lecture notes or all this is just in order for you guys to focus on the lecture. Okay, so now this row is this form. Row is this form. Okay? Row is this form. And then row y. And then we try to commute with this one to bring this one to here. And this is dagger. Xn minus 1. And then row s. Row y, sorry. Row y. And minus 1. Like this way. So since this row is side dagger psi, so and then side dagger and psi will have a non-trivial computation relation. That will give you this delta function. That will give you delta function. Okay. So if you use this one, so if you apply this one to here, what you get is just the influence. You write down. So this part, yellow part. So this yellow part is equal to y minus xn, and then side dagger xn Side dagger xn minus 1 and row of y, and then side dagger xn minus 2, side dagger x1, we have some factor. In addition to that, we have this term, cube y, by minus xn, and then side dagger xn. And times okay, so that's what you get. Okay. So this part is okay, maybe it's better to do yeah. So this part is replaced by this part and then this part. Okay, like this one. So now you can see that the second time you can perform the integration by y. If you do the integration by y, what you get is the second term. Okay. Now different color. So the second term is equal to b xn minus 1 minus xn, and then the rest is just xn to x1. So therefore you can just write down like this way. The red part is just b xn minus 1 minus xn, and then is it okay? So because we just the function just substitute y equal to n minus 1. Okay, so then now you just do the recursive. So it was row was just a bit right next to the xn. Now here you have row is right next to the xn minus 1. And you just repeat this, next you commit with this guy and so on. Okay? And eventually row will hit here. Okay? Then since this is the normal order style analysis bucket, so therefore eventually you get a 0. But at the cost of commuting, you always get this red part. Okay? So therefore, what you get is that this yellow one, yellow part is equal to just the sum of b x I minus xn line correcting. Let's see. Margin correcting. Xi to the x1. I one to n minus 1. Is this okay? So is it okay? Is this okay for you guys? But not how. So this is the only yellow part. The next you have to look at the first one. Okay. The first term is just okay. The first line is just b is left next to this xn, but here b is left next to the xn minus 1. So you can do the recursively. So now you just bring b half into here. What you get is that instead of y minus xn, you will get the xn minus 1. Okay? So this purple one is the side dagger xn. psi dagger xn minus 1, then b of y, and then x psi dagger xn minus 2, psi x1, absolute 0, and plus dy, dy minus xn minus 1. Dagger xn minus 1, and the row of y, and the psi dagger xn minus 2, psi dagger x1, and 0. Okay. Okay. So the situation is very similar to what we had before, but now row is just right next to the xn minus 1 instead of xn. Okay. And do the same operation. So then what you get is that so this part is just similar to this yellow part. So let's do the wavy yellow part. The wavy yellow part is just sum of I is equal to 1 to n minus 2. Okay, b x I minus x n minus 1, and then x1 xn. Okay. Okay, so that's what you get. This means nothing, and then you just repeat the now first line too. And what you get is that eventually what you get is that here the half is equal to sum over I greater than j, b x I plus xj, and then x1. That's what you get. So just condition is that I greater than j. Any question at this moment? Fine. So the dimension we treat Hamiltonian sum of as an operator that acts on Hilbert space. The operator acts on some state. Okay? The acts on state, and if you get what kind of operation it acts on, or acts on Hilbert space. Operator acts on Hilbert space. Now you have the often you get another insight. So to understand this interaction and so on, you can have the following thing. So the space correlate to momentum constant. Usually, if you go to this space coordinate, momentum coordinate, you understand you get some another insight. For instance, the space, this is just Fourier transformation. For instance, style sigma is the k. Okay. For this sigma is the can be understood as spin variable, or some other quantity, some physical quantity. Okay. And the dagger, if you have a dagger, so this yellow part, just dagger. Like this. And then last time we thought of the decay. So here we treat as an ferment. If you treat it as a ferment, is equal to okay, like this. Okay, so this is a commutation relation. We treated the operator, so the Fourier model is also operator. Sorry, there's some two files here. Okay, and then we can take this interaction term is also Fourier transformation. E to I and Q x minus x. Then, so this interaction term we have can be written as follows. B hat equals to plus sum over sigma prime, and then product for K1 integral 1, 2, 3, 4. Okay. Maybe product of dki to the q equal q I equal to 4, 1 to 4. And then you have a BQ, and then CK, 1, sigma 1, sigma target, CK 2, CK 4, 3. I mean, just the convention prime, dagger CK 2, sigma prime, and CK 1, 2. Okay. So that's Fourier transform of B hat. Okay. Alright. So that means something. In fact, this one is e times d x cubed, d x prime cubed, and the e to the I k1 minus k4 of x plus q. Plus q of x, and the e to the I k2 minus k3 plus q of x. Is it okay? So it used to be, I already read it used to be dq, x dq, x prime, e x minus x prime, and sine dagger sigma x, sine dagger sigma prime of x prime, and sine dagger sine sigma prime of x prime, and sine sigma of x. It was like this. And then you just do the Fourier transformation, you get this. And now you can perform Fourier transformation for this part. This part, you can do the Fourier transformation. I just perform integral. This will give you the dot function. Like this. Okay. Okay. So then what this means is that the following. So what it means is that the so if you add this E hat on K1 and K2, K1 and K2. So recall the sigma dagger K1 or K1 sigma and K2 sigma prime. So recall that the K1 sigma acts on vacuum is equal to K1 sigma. Okay. So this is one particle step with momentum K1 and spin sigma. Sigma can be plus minus 1 half. Okay. So if you do act on that, so this just analyze the analyze this analyze the effect. So this means that if you start with the particle with momentum K1 and sigma, and here you have a K2 and sigma, then sorry, I think the sign's wrong. So this is the minus sign. So this should be minus sign. This should be minus. This should be minus. So then what you get is that you just omit the particle momentum q, and then here you have the K2 minus q, K2 minus q, which is K3 sigma prime. Okay. And here instead you have the K4 is equal to K1 plus q, and then 6. So this interaction term in momentum space would is that the interaction between particle 1 and particle 2 and exchanging some momentum particle with momentum q with amplitude V of q, and then you just need integral over V of q. I think I mean. Any questions at this moment?
C is basis on momentum space.
Yeah. C is the Fourier transformation of the this one. This is space coordinate. This is the momentum coordinate. The operator. Any question at this moment? Okay. That's that. So this is called final diagram. This is called final diagram. And then if you take QFT, you can learn much more about it. But remember, this is no QFT course. So one student asked when he doesn't learn QFT or he doesn't learn or she doesn't learn quantum mechanics II. So, but it's fine. I mean, it's only necessary part is the one we are learning now. So I mean, you don't need to worry about it. You don't need to know about all the knowledge about quantum mechanics II or QFT and so on. So what we need is just that only second quantization we are learning. Any questions at this moment? So now, let's look at the different examples. different example. So, for instance, if you have the particle interact with the delta function, example. Okay? So if E of x is some constant times delta cube of x. Okay? So if you write down like this way, so if you go to momentum space for your transformation, E of cube given by constant d cube x e being kind of I cube x, and which is equal to just constant. Just constant. So therefore, what you have E hat is equal to sum over sigma and sigma prime constant times C dagger K1 minus Q C dagger K2 plus Q sigma prime sigma and C K2 sigma prime and C K1 sigma. So and then you just need to integrate abruptly K1 and Q. And then most likely Q2. I think I missed in fact there must be something like a P of Q, and then you must have the Q equal. This is what I missed. So that's the potential operator if you have a delta function in momentum space. Okay. Any questions? Let's look at the more physical potential. For instance, the P is equal to E to minus lambda R over R. So this is for Yukawa coupling, Yukawa potential. So I don't know, long time ago, like almost 100 years ago, Yukawa introduced this potential to describe the interaction between pi x. So that's why it's called it. So the important thing is that the Coulomb is the 1 over R times some constant. I don't care about constant at this moment. That has okay. So let's put that constant A. And this is Coulomb potential. So this is 1 over R, so inverse to the radius. So therefore, interaction goes to long range. But here you have an exponential decay term with radius. So therefore, it's really like short range potential. And then let's do the Fourier transformation. If you do the Fourier transformation, and this is just E of Q. Of R. E to minus I cube of Q. Okay. And then since this is the R is a radial coordinate, we just perform to the radial coordinate. So then what you have is that the 4 by r square r and d of r. So and what's left is that the okay, so sorry. S e to the minus r over r, and then here you can have that the so 1/2 minus 1 equals theta, and e to the minus I q r and cos theta. So here q here and x is here, and this is theta. And then, of course, dq x is equal to 4 pi r squared dr and d cosine theta. I mean, you used to have, sorry. Yeah, r squared and d phi. But now, there is no phi dependence. Phi, I mean, it's a rotational invariant around the Q. So therefore, you can perform d phi, so you get the d phi. Okay? And then 1 4 pi and then 1/2 cancel. So that you get 2 pi. And if you do this integral, this is in fact is equal to okay. So therefore, this is equal to and if you perform this one, you get the 4 pi a q squared plus lambda squared. So this is a Fourier transformation of the equal potential. Okay. So therefore, for this one. But if you set lambda to be 0, you can't become true. So therefore, essentially, Fourier transformation Coulomb potential is 1 over q squared up to some point. Okay. Any questions at the moment? So those are treatment of the interaction. Now. Okay. So now we fit the Hamiltonian and also the inner operator function as operator. So now we consider some n particle state. So you can consider the n particle for last time particle state. So n particle state is some overlap between electrons. So of xn is psi of the t. That's what we learned last time. Okay. So this is the overlap between some wave function and with the n particle state. Okay. So this is essentially zero of psi of x1, psi of, and then have a psi of t. Okay. And in fact, here it's you need to use the hardware picture. So even like psi operator would depend on t. Psi x t is e to the I h t the psi of x. So this is the what we are showing the hardware picture. I don't remember the sign is issue. And then so implicit depends on t. So this is the wave function. Wave function. In function here. And then this will satisfy the Schrodinger equation. In quantum mechanics, what you learn is that there's something like a I del T of psi delta T is given by HD of plus B. B times E star. So that's the Schrodinger equation. Well, how many times? Or maybe some time. So this is a many-body Schrodinger equation. Maybe many-body. Schrodinger equation. So now we try to derive this equation by using second quantization scheme. So recall that this H in this is the second quantization. So H is given by sum of sigma and d cube x. Like this way, plus 1/2 e x minus x prime, rho x prime, and rho x, and then normal order. We have a normal order. So that's the Hamiltonian. So this is the operator. And now we treat everything as a operator, but and then in Heisenberg picture. Heisenberg picture. Sorry, I think I should put the sigma here. I mean, I don't get sigma at the moment. So the Heisenberg equation in Heisenberg picture is given by I times del psi del T is equal to H dot psi. That's Heisenberg equation in Heisenberg equation. Now treat this psi also implicitly depends on T. Implicitly depends on T. Everything is Heisenberg equation. So this is the free Hamiltonian. Not free, sorry. So this is single volume Hamiltonian, HC. Okay? And this is interaction. I call it statistics. And they use canonical quantization to compute okay. To compute this computational mission, we just use the following fact. Psi of x and the psi dagger of x prime and all x prime psi of x prime is equal to, we just have this computational relation between psi and psi dagger. So if you use that, you get the delta cube x minus x prime or x prime sub x prime. And then also we can have a psi of x and the rho x and x1 and rho x2 and normal ordering computational relation, you get the delta. So essentially this way is psi dagger x2, psi dagger x1, x1, x2, and psi x2, psi x1. Okay. Therefore, what you get is that the delta x minus x1 cube and then rho x2 psi x plus delta cube x minus x2 rho x1 and psi x. So the first term is the computational relation of psi of x and then psi dagger of x1. The second is coming from psi of x to psi dagger of x. Okay. Psi dagger of x. And is it okay? This something strange. So if you compute with psi dagger x1, you get this one. So these are rho or x2, and this is psi x1 is the by delta functions, positions. So if you use that, maybe I can. If use this one. But x is equal to minus delta square sigma m plus e of x plus of psi of x. And then psi of x and b is equal to e cubed x prime e x prime minus x like this. That's what you get. Is it okay? And then H is just H0 plus B. H0 plus B. So just sum over this. And now we plug this one into here. plug this into here. Because these sides are operated. So therefore, our Schrödinger equation can be just obtained by Schrödinger equation is the I times delta capital psi of the t is just the sum over j equal to 1 to n 0 psi of x1 del psi x2 xj del t xn and the psi, capital psi. Okay? Okay, and use this quantization ratio. So del psi del t is given by like this way. Then this you get. So you get this one is equal to sum of j and minus del j squared divided by 2m plus u of xj psi x1 also xn and t and plus sum of j x prime cube dx prime minus xj and 0 psi x1 psi xj rho x prime. So rho x prime psi xj psi xn and capital psi. Okay, so that's the interaction. So you have a sub-integral with d and rho with But this one is exactly what we already saw before. Okay? This part is exactly how t acts on x1 over xn. And this is we already saw that this one is equal to sum over I and j dx of I minus xj with corresponding state. Okay? So this is exactly what we have. So therefore, therefore, I don't want to rewrite everything. So therefore, this red part is essentially sum over I equals to j dx of I minus xj and then psi x1 equals to xn and t. So this is it. So if you use the second quantization Hamiltonian and use the computation relation, you will get the many-body Schrödinger equation. This is a many-body. So this is the Schrödinger equation for single particle. Okay, single particle. This is the interaction between the other particle. Any questions at this moment? So this is the Any questions at the moment? If not, I'm going to move on to the next topic, which is you are already familiar with. Statistical mechanics. Statistical mechanics of linear. That's it. Can I ask one more time? Does anyone have some adapters for video? Does anybody in this audience? I want to connect this one to MacBook. No, nobody has. Okay, unfortunately. Okay. Then the next time, I think I should buy and bring it. Sorry. This time it doesn't work. Okay, so the goal of this the goal of this section goal is that the to describe the thermal so to describe, sorry, to describe by statistical mechanics. Well, in particular, so we just consider the following. So the potential entropy and also energy, internal energy, and then heat capacity versus temperature. How do they behave? Like this way. And in particular, and we just take the limit of high energy and low energy. High energy, high temperature, high and the low temperature limit. If you take a low temperature limit, and then they and both bottom determined. In particular, what's more interesting is this, of course, you want to understand high temperature limit or low temperature limit. Which one is more important? High temperature or low temperature? So low temperature is more important. Okay. So that's what we are doing. So that's the goal of. Okay. This material is already you already learned in the stat mechanics one, I guess. But let's do one by step by step. Okay. So first of all, in particular, so this is the Einstein conversation. Einstein condensation. And also here is the Fermi. And also it's called Doppler distribution. So that's we are going to go on now. Okay. Okay, given the state, statistical state, or many-body state, or whatever, um, statistical quantum state. Given, so we can have a number. It's given by sum of Q and Q. And then energy is the total energy is the total number and total Q and epsilon Q. Okay. So for instance, so this is total number and total energy. For instance, in boson, so let's see. Boson you can have energy state like this way. You can have many. Like this. So NQ means so this N0 is equal to 4, and 1 is equal to 3, and 2 is equal to say 0 and so on. That's one. So at the each energy level, Q can be understood as the energy level, and you just sum over everything. So this is Morgan case. For fermion dimension, so each energy, each state, you can have only 1 or 0. Like this. So then 0 is equal to 1, and 1 is equal to 0, and then 2 is equal to 1. And then here, so total energy, so this is the E. So this is E0 is E0, E1, E2, E3, and so on. Okay, that's what we have. And the sum total energy is just sum over each state times number of the oscillation number. So quantum state U is just a 0 and 1. And like this. You can describe like this way. Okay. And now, so we consider the ground canonical ensemble. Consider ensemble. So ground canonical ensemble, and consider the partition function of G, which is sum over total nu like this. Nu times and G. And this can be represented as follows. So to plug this one into here, what you get is that the Okay, I just plug this total method, and you have to sum over all possible configurations. All possible configurations. So this one can be understood as follows: all possible configurations, and this one can be understood as the sum over product of Q, the product of the Q, and the E to minus layer is from Q minus mu times NQ. So in bosons, you have whatever. So these states correspond is described by Q. So you have to transfer all possible the I mean previously it was like this way. So this expression, if you just write down, this is times Q sum over NQ. Sum over sorry. So like this. Sorry, let me see. Oh, it's okay. It was okay. Okay. Yeah, I mean also okay. Product of like this. So now boson can take any possible value. So for instance, this Q is a boson product of Q. And it's boson, so you have 1 plus NQ can be 0. The next is minus layer epsilon Q minus mu. And the E to the minus layer epsilon Q minus mu times 2. So integer number. On the other hand, so this is boson. So fermion, so you have 1 plus E to the minus layer epsilon Q minus mu. That's it. That's it. And this is fermion. And this is equal to, if you use the geometry series expansion, this is minus layer epsilon Q minus Q. If you use the geometry. So therefore, in convention, you have Q 1 plus sigma E to the minus layer epsilon Q minus mu times 3 sigma, where sigma is equal to plus 1 for fermion, sorry, minus sigma and minus sigma. So this is boson, sigma is minus 1 for fermion. This is both Fermi distribution. This is for both Fermi distribution. This is, I think, you guys are very familiar with. And this sigma can be understood as the once you swap the two particles, whether you get a plus sign or minus sign. Okay, this is permutation sign or boson permutation. And therefore, so this is the this is grand chemical ensemble. Potential function different, and then from potential, you guys take a log of this. Log of this one is this is essentially sigma over beta sum of Ln 1 minus sigma E to the minus beta epsilon Q minus Q. So this is the sum over Q. So this is a ground potential. Okay, so now we need to record the following thing. So we record that omega delta mu fixed EB is equal to minus n, and also U internal energy U is given by del P log Eg Newton's N. Okay. Like this way. Okay, so then, so if you use this one, what you get is follows. So n is taken derivative with respect to mu, right? Yeah, mu. With respect to mu, what's going to happen is that the sum over q you take the mu and then 1 over e to the beta epsilon q minus 3. So that's what you get. Is this okay? Yeah. So that's what you get. And I call it this one is the so this one is I call it this one is mean oscillation number and half and vacuum. So this is the mean oscillation number of single particle state. Mean oscillation number. Of state Q. Now you can do the same thing for U. So the gravitational potential is given here. So that therefore take the derivative with respect to theta. What you get is that this one U is equal to sum over epsilon Q, and then same quantity should arise here. X and Q. Okay, so you just apply it. You just apply beta derivative on here. Then you get exactly this. Is that okay? I think we're ready for you guys to eat. Okay, let's and then so this is the Wolf and Fermi distribution. So this n bar is the distribution. Fine. Let's move on. So if you take high temperature limit, so high temperature limit is minus mu greater than 1. You take this is the high temperature limit. So then, so if this is a big, so this is dominant than the sigma. This is just one. So therefore, what you so L bar Q is roughly e to the minus beta epsilon Q minus 3. So this is for Maxwell and sometimes include Boltzmann distribution. Is there something strange? Okay. Okay. And let's move on. So S can be obtained. Then B. So thermodynamic quantity, and this can be understood as the TV. Okay. So then you can use the derivative of omega. Omega is written over there, and take derivatives, which derivative with respect to phi. And what you get is that the as follows: the KB. I don't like KB, but Q minus sigma log. Okay, so like this. And then this part can be written as the follows: the log 1 plus sigma am I am I doing the right thing? Divided by minus n and q. Am I correct? Okay, let's do the computation. I didn't do this computation, that's why I got confused. Log and q. Okay, so then let's do the computation. So it's just a simple one computation should be right. So this one should be e to the beta epsilon q minus mu minus sigma divided by one plus one minus sigma and e to the beta epsilon q minus mu minus sigma. Is it okay? Do you agree with me? Is that okay? of course, like this way. So this is numerator, the denominator is just the opposite of this one. So this is okay. And this one is equal to e to the beta sigma. Sorry, e to the beta is from q minus mu. Okay, is it okay? So therefore, if you take a log, you will get this one. You get the log. Fine. And if you massage this equation, you will get as follows. If you massage this, then you will get this one. This one is equal to kb is equal to sum of q minus n bar q log n bar q plus sigma n bar q and then log 1 plus q. It's infinity. So that's that. You massage that. Okay. So that's the what you get from. Any questions at the moment? Yeah, so everything's okay. So this term come from essentially here times this one, and this term come from here. Sorry, here, and then this term come from this one. So this. I hope you understand. So this is the entropy by using this bold and perfect definition. Okay, and then finally, we have to derive this heat capacity. Heat capacity is the is the given by d delta s delta t. And we derive already s here, and just derive derivative with respect to t will give you the equation. And it's fixed. And this will give you sum over is from q minus e and del minus q del t. And which is given by e. X plus 1 kb del mu del t. Yeah, so this one depends on E and mu, right? T. And this is equal to del mu del t. X times EX divided by sigma squared, where X is equal to beta. It's confused. So this is just a simple calculation of the derivative of in the S. So here, derivative S into here. Any questions at the moment? And I mean, you have to do the honest calculation. I mean, so since there is a P here, so P here, del T will see about the here, and also mu here, and also beta here, and mu here, beta mu. Actually, if you take the derivative, they cancel each other. And then what's left is derivative with respect to p in this distribution. And then you get it. So I mean, this one you have to do the calculation by yourself. I'm not going to do the. And plug this one, this quantity into here, you get this. Yeah. This. I mean, it's just I mean, it's kind of tedious, but you have to. Okay, so those are the C, S, and so on. Okay. And we try to look at how they behave under the temperature from now. Okay, let's take a break. Let's take a break. And if you have an adapter for this one, just give it to me.
哎，有些东西我还是像那个分离子，它那带来的我其实都是很高的。
想画一个那你没两个名词的讲过，还有讲过的一个，但是跟到腰面这么健康，那我都是这个低吗？这个会有点。其实我这打那会我在给也宣传的理解的。
会遇到他马达分。对啊，coming soon。哦，good，棒。
有可以的地方。我是一样的，把中间这一部给展开，然后它中间当中给讲这个中间全部可以走，那是还有多钱？是啊。我的就会干啥？我做一个
我是以
对。没有水准的学。
我们
对啊，对啊，八个人谁干？也确实。然后，但是因为他是。所以说没有。好，因为 depends on 对啊，你把A 和 B 的孩子在地方都，然后把它用一个这个然后得到 B 应该保留吧。可以保留，对，然后你就得到 DS 这个第二题就是对这个情况不好，都算。Non-foreign operators 是这个我个人个企业的这个企业的这个疫情。是的。到我们是西洋这个设计，我们是讲话要不我们再一起。都发出来，他不写，因为 对啊，他以前卖我2块钱一个，但他太顶高，感觉比你的被搞得我哦，其实他这是非常最好吃的，你搞不懂搞不懂，今天做一个我以为那你也可以，不要很难，现在都2.5，对，还有或者说取那个单位，然后我们这个单位。你说他们因为单位的关系，然后说这一坨的单位的我觉得中间是一个非常肯定的。我们看回来评价的。这样你需要算一遍1把到再明天再请。OK， 我按他半天发给所有的点，你看看不对。为什么一堆都算？你还是灰色。Yeah. First of this,靠海的那边去了。我每次下假山买菜，我操！最狠的时候报应和鸡蛋，真正做了2个半小时，也他妈的非常有鸡蛋壳，一颗没碎，用半个月的鸡蛋，问题了。对，直接好美的。简易的蛋就不会蛋，不蛋就会不蛋，这蛋这个蛋怎么？而且是当地的只是饭点题，还有那个只有在湖北吃的不够的。对，七区零的时候特别经典的叉烧，其实是对，很熟悉，确实。OK， 完美。现在我们可以回头看这几部美术，这几部都是走到了对。别见。OK， 很多次。好，
有可能是美，这是100斤。那个看一下语言，跟我学的是。
Okay. Shall we? Okay, so the one question about the second quantization quantization. Then in my lecture notes, I put the mu here. I didn't explain it. Usually, in quantum theory and so on, like many-body systems, particle number is not like conserved. So therefore, we have to use a grand canonical ensemble. So precisely speaking, we have to use the usual E minus mu n for grand canonical ensemble function of n. And n is the just given by d2x rho f. So this is density operator, and this is the speed measure number operator. So therefore, precisely speaking, I have to include this minus mu if you work in the grand canonical ensemble. And then, yeah, that's what I want to do. Yeah, and of course, sum over sigma. We have to include that's one comment. Okay, so thanks to that, I have now show the behavior of the particle. Maybe it's better. I don't know which one. Okay, let's do that. So here, you chemical potential, appropriate normalized, and then S is the entropy appropriate normalized. Use the internal energy of the system, and then see the heat capacity. And if you use so we derive everything by this Bose-Fermi distribution by grand canonical ensemble. So these are the plot in terms of temperature. And this dash line is the just use the thermodynamics. You just thermodynamics. But the solid line is use this grand canonical ensemble and use Bose-Fermi distribution. So that's good. We'll look at the one by one. So from here, the first of all, so if you, there's many things we can predict, but for instance, the entropy, if you use the grand canonical ensemble, entropy becomes 0 when temperature is 0. That's what we expect. But if you use the thermodynamics, it goes to minus infinity. And also, so here, this is chemical potential. As you can easily see, chemical potential for both is just keep 0 for a while. Okay? Keep 0 for a while. And unfortunately, it's gone. Because I think I should connect the fine. Hopefully, if I got the battery, so the charger, it should be okay. Hopefully. Anyway, so let's see what's going to happen. Okay, then now so here you just keep both have a for a while you have a zero and it suddenly drops to the negative. So this zero region is so-called the both Einstein condensate have to occur. The same thing happened here. So there is some phase transition occur here at the same temperature. You know that both Einstein condensation will start occurring. So all majority of states just go to ground state. And the important thing is that for heat capacity, if you go to high temperature, it just approaches 3/2, it's 1.5. That's also one thing. So another thing is that for internal energy, if you go to high temperature, it becomes linear in temperature, linear temperature. But if you go to low temperature, the behavior is no longer linear. That's what we are going to see from now. What else? Those are the prediction from quantity. Hopefully, let me. And anyway, so if it is off, it's okay. So we will try to derive this property by looking at this equation we derived now. So now should I okay. So so we introduce something called single particle density state. Okay, single particle. Density state. Density of state. Okay. So this one is essentially not this from minus 6 from Q. Well, okay. However, so suppose the system, suppose system is box Q. System, the ideal gas in the Q with length S. Okay. So then the momentum can be quantized. Momentum quantized in the everything in D. Okay. Then so this one is equal to essentially And you can have a spin 2s plus 1 in total degeneracy, and then L over 2 pi of Q, which is the so here you just insert here is delta K Q over 1 delta K. And then here you have half over delta K Q. Delta is minus 16K. And this is roughly speaking, so this is big in degeneracy. So essentially what we have is J minus 1, maybe S, I don't know. Anyway, J minus J is essentially 2J minus 2J plus 1. And I just changed the variable J to S. And then 2S plus 1 and over 2 pi of Q, okay? Q. And instead of sum over K, just write down in terms of integral, dqk of Q is minus 2. Okay, then adopt the polar coordinate. What you get is that the 2S plus 1 of Q 2 pi Q or pi, and then equal to infinity dk is here. Alpha. Okay, so polar integral does not is independent of polar integral, so that will give you 4 pi. And this one, and K is essentially 2m epsilon K square root of. If you have an H bar, if you want, you can include H bar, that's okay. No, square root. Or on top. So that's how I do here. Then this one is equal to S plus 1. Instead of a cube, I just write down volume and divide by 2 pi square and m over h bar v over 2. And then 0 to infinity epsilon k. Epsilon k 1 half. And the epsilon k delta epsilon k. That's what you get. And if you perform integral, so you will get 2s plus 1 b 2 pi squared m over h bar e over 2, and the other function just give you the this is 4 pi. The other function just give you epsilon 1 half. Okay. And to make sure that epsilon is positive, you can add the Hepson step function. So this is ensured. So Hepson step function is as you know, so like this step function. So that will ensure that the epsilon is the positive. Okay. In general, for this 3 dimension, in general, for density, general dimension D, in D dimension, this is proportional to volume times e to the e minus 2 over 2. So that's that. Okay. Fine. And then now, so we can just write down this one. You see, N is used to become over Q, and Q. But now we can just write down this is minus infinity to infinity d epsilon e to the minus n. Okay? U you can just write down like this. It's insert the SL product, which used to be just the dot function. Plug up into here, we can just okay. So now we'll take if you use the merit of the density function that is suppose. Okay, so density function, I call this one A. After A. I don't like the too big to write. I call that this one is equal to A as a constant. So then, so it is from some numbers we obtain this one, ED times is equal to minus omega. And this is equal to, we already saw this is better, 0 to infinity. If you use this single particle density of state, so this dE, E of E, log of 1 minus sigma E, which later is 1 minus E. So now, for just substitute this one is equal to A times E to the what? 1 half. Oh, sorry, E to the 1 half. Like this way, then what you get is that the minus sigma A over beta 3 over 2 E to 3 over 2 log of 1 minus sigma minus E to the minus A is minus E. Like this way. And then, so I just do the integral by part plus sigma A beta 0 infinity. Oh, sorry, that's beta 3 half. And the E to the 3 half. Like this. So this is the integral part. So suppose you have big derivative of epsilon, and which can act on either this one or this one. Either this one. So now, let's look at the first term. First term, sorry, no, it's not E. E is like this way, sorry. This is energy. First term, so when epsilon is infinity, what's going to happen is that so this is equal to 0, okay? This is equal to 0. Log 1 is equal to 0, so this should be 0. If you plug 0 into here, this is 0, so this is 0. So the first term is irrelevant. The second term, sorry, I got confused. And this is equal to 1/3 of 0 to infinity d3 over of e to the layer of epsilon mu minus sigma. So can you see that? I mean, just multiply this one into downside. Oh, sorry. I think I made a mistake. Is it okay? Yeah. Oh, it's okay. So instead of this one, you just multiply in here e to the beta epsilon minus mu. Okay. So then, and we know that a times e to 1/2 is the e of e. So that's what it is. So this one is just a 1/3/2 of internal energy. Okay. So therefore, so minus of the ground ensemble, and then you get the so this means that the PV equal to 2/3. So this is the very famous equation for ID gas. Yes. ID gas in the box. In the box. Very famous equation. And then this 2/3 is really coming from the dimension. So if you want to generalize the dimension, this becomes the general dimension of this is 2/d over u. So if you generalize the general dimension of u. Okay. Any other questions? Any questions at this moment? Okay. So now then I will introduce something called dimensionless quantity. Dimensionless quantity. Okay, I think there are lots of mistakes in my. Okay, I think there are lots of mistakes in my lecture, unfortunately. Okay. Okay. for instance, so this. Yeah, as you can easily see from here, so density. So here, so here it's just the density conduction of uh, some metal. Some metal is given by density is given by like 8 point. Sorry, I just got confused. So what I want to say is that the here density is very high here, even though the heavy liquid and also very small. Okay. Conducting electrons very small, and in particular, so quantum temperature scale is very different. So very different. So this 10 to the fourth, but like here you have the EQ is the So here it's very small. It's very small. So therefore, I think you have to. I mean, even though we can treat those materials as an ideal gas, we have to appropriately normalize to see the universal behavior. That's what we are going to do. To see the universal behavior. Okay. So to normalize it. To normalize it, so we have to introduce something called character selection. Characteristic. Yeah. So here, so as you can easily see, so in the vertical axis is appropriate normalized here. So appropriate normalized and characteristic length for each ID gap. So LQ is equal volume divided by n, and then divided by degeneracy of spin, and then you have one here. So this is the characteristic length scale, and then KQ characteristic length pi over LQ. And then epsilon Q is H squared Q squared divided by M. And temperature Q is epsilon Q divided by K. That's the characteristic temperature. So as you can see here, EQ here is the characteristic temperature for the conducting electrons, some metal or liquid. So it's a very different. And so therefore you have to appropriately normalize to see the universal behavior of the ID gas. So as you can easily see, so here, let's go here. So this horizontal axis is normalized by T over T cube. So T over everything normalized T over T cube. So to see the characteristic behavior of the ID gas, we have to appropriately normalize like this. To do that, okay, so that's particle number condition. So if you use the, so therefore we appropriate normalizing. So epsilon theorem is the epsilon over epsilon q, and then T theorem is the pi. Yeah, it's okay. T over T2. And the mu is given mu tilde is given by mu over epsilon q, and u is given by so u tilde is given by u divided by n epsilon q, and c tilde is given by p over n times k. So in this way, so we just normalize appropriately, and then see the tilde part. So we use the later on we use tilde variable to see the behavior of the tilde variable behavior of IDLs. So the normalization will so if you use this normalization, so the particle number we derive under condition will give you the following equation: 1 is equal to I mean, this is just a simple calculation. Okay. So let me write down 2s plus 1. I mean, it's just simple calculation. 4 by third n. H plus third. 3 over 2. And then epsilon tilde on top. And e to epsilon tilde minus tilde divided by t tilde. Tilde is 1 thing. And plus height, all the EQ into here, EQ into here, and then use this definition for LQ. Use this definition LQ and the EQ into here. You can show up the distance. This part will simplify pi over 4 first. Pi over 4. Pi over 4. First.
2s plus 1 also
What? So essentially what I need is this is plus. Oh. And also, so we derive this all the quantity in terms of the using the boson Fermi distribution. So we derive. So this is the n coming from n, and then the u, and you have to rewrite everything comes from pi over 4, and then 0 to infinity. This is from 3 over 2 tilde, and then e to epsilon tilde minus mu divided by t minus 6, and e epsilon tilde. This is u and c tilde. We also heat capacity derived, and this is pi over 4, and then infinity of 0 x minus down u tilde down p tilde, and then x e x e x sigma squared and 2x e tilde minus tilde divided by p tilde, and then p is constant. So that's the normalized heat capacity. And then one more thing is that the I don't think I have space. Okay, then let me erase. So del mu tilde del T tilde. Okay, del mu tilde and del T tilde is also derived, right? Oh yeah. So you can use this guy, this equation, and then yeah. So this equation. So this equation. So now this equation del T. Okay, del T tilde. If you use del T tilde, well, you can derive. So this left hand side is of course 0, and right hand side, what you get is the following. Okay, let me erase here now. So if you do the derivative, so left hand side is 0, and right hand side what you get is I over 4. And then essentially you have epsilon tilde on top e to the x over sigma squared, and then x e x, and then divided by d. And the x is equal to epsilon tilde minus e tilde divided by t, epsilon tilde plus del mu tilde del t tilde, and then here you have the pi over 4, and then epsilon tilde on top, and then e to x divided by e to x minus sigma squared, and then x is equal to the same u tilde divided by t tilde and the epsilon. So that's equal to 0. So this equation you get. The first term is just like fit the delta t tilde into here, into here. Then you will get this quantity. And the second term, you just hit the delta tilde into mu here. Mu here, then you get this quantity. And then if you just rewrite this, so you just have this is gone, and this part is essentially become divided by minus pi and then divided by epsilon tilde of half e to the x minus sigma squared, the same substitution is equal to del mu tilde. Okay. Fine. So this expression necessary for this time, for this heat capacity. And so for heat capacity, we need to just plug this one into here. Fine. Now, the first, let's do the easier one. Okay, so using this how to say relation, we derive we try to see the high temperature, low temperature limit of this ideal gas, like a limit of thermodynamic quantity of ideal gas, and how they depend on the temperature. Okay. Okay, now then, I think let's look at temperature. Temperature T T over Q is very big. Then this means that the high temperature limit means the T to the minus epsilon tilde mu tilde divided by T tilde is very small. Okay. So we can just do in terms of we just need to expand this variable, very small variable. So instead of writing this one, so you just take the opposite inverse scheme. Okay. So let's look at this one. This one is equal to 1 is equal to pi over 4, equal to infinity, epsilon tilde 1/2 e to the minus epsilon tilde per tilde divided by t tilde, and you have a general series. E to the minus epsilon tilde minus mu tilde and t tilde. Okay, and then plus e to the minus 2 times epsilon tilde minus mu tilde and t tilde plus dot dot dot. Okay. So what I get is the equation x minus sigma epsilon tilde on half is equal to x inverse 1 minus sigma x inverse epsilon tilde and epsilon tilde x inverse 1 plus sigma x inverse plus sigma x inverse plus q plus that's what I do. Is it okay? Okay. And then since these are very small, we just look at the only like a first leading contribution, and this is equal to pi over 4 into the cube over 2 e to the mu over t tilde, infinity x 1/2 e to the minus x dx plus sigma e to the mu over tilde t tilde and 0 infinity x 1/2 e to the minus tx dx. Here is e tilde is equal to t tilde x. That's fine. Now, so this guy is in fact equal to the gamma function. This is equal to the gamma of e over 2, which is equal to square root pi over 2. And this guy is equal to gamma of 5 over 2, which is what? 0. But if you know this one, you can derive this one. Mass by what? Mass by what? 3 over 2. 3 over 2. First pi over 2. Fine. Therefore, this is equal to 1 is equal to roughly Newton 1 plus sigma okay, that's what we get. Newton. I mean, if you're sick, I think it's better to take a rest. I mean, okay, from this relation, so what can you derive the relation between mu theta and t theta? So mu theta is given by the minus t theta and the log I mean 3 over 2 t theta log by t theta over 4 plus t theta minus log 1 plus sigma e mu theta t theta divided by 2 to the 3. Okay? And then we can approximate this guy is this guy is approximately equal to sigma e to the mu theta t theta divided by 3 over 2. Okay, so then by Taylor expansion, and then just simplify it. So from there, you can have e to the theta over t theta equal to approximately equal to 4 over pi t theta divided by 2 to 3 half. So this is a leading order behavior of the mu in terms of t theta. Fine. So high temperature limit here. Oh gosh. So high temperature behavior here, around here, is described by this equation. This equation. So furthermore, oh yeah. So then now we have a relation mu theta and t theta. We can plug back into here and then perform calculation. Likewise, you can do similar analysis to do the expansion. So the upper one, lower one is just a power of this here. 1 over 1/2 becomes 3/2. Yeah, 3/2. Okay. And the computation to that is n. So computation is exactly similar. So utility is roughly speaking 3 over 2 utility 5/2 divided by 16 e to the utility over t tilde 1 plus sigma e tilde over t tilde divided by 2 to 5/2. Okay, if you compare with previous equation around here, I mean, instead of 3/2 here, you have a 5/2, 5/2, and 5/2. And some appropriate coefficients need to be changed. E over 16. Okay, and the thing, you can see, we have this relation. We have this relation. Plug back into here, and then you will get the sum over 2t tilde 1 minus sigma square root 2 and the pi. Okay, so that's it. Okay, now if you look at this utility, so if you go to high temperature limit, the leading behavior is linear in T, linear in T tilde, and then the leading correction it depends on boson ferment. It's different. Boson you have a plus sign, so therefore it have a it's dash right minus a little bit. It's negative. And then for fermion, so you have a minus sign, so minus sign minus to plus is a little bit above. Okay. And the slope is slope is 3/2. Okay. So that's the table. Now we can do the same exercise. So we plug that into here. So and then perform the integration. So the plug this relation between T and plug it into here. Yeah. So essentially heat capacity is D U tilde double T tilde like this way. And then what you get is this is 3/2 1 minus okay 1 minus sigma square root 2 I square root double T is here the 3/2. And then if you divide by this, and then here, what you get is that you do that, you have a 3/2 exactly same time. So therefore, this is the 1/2, 1/1, like this. Is it okay? So derivative to T and derivative to P, and they combine, and you get this. Fine. And then you get the C. If you look at T tilde, so the leading behavior is exactly 1/2. No, 3/2, 1.5. And depending on the sign here is the opposite, plus sign here. So therefore, boson become above of this 3/2, and the fermion becomes below of this 3/2. So therefore, it's a perfectly nice behavior. Fine. Okay. Okay, so that's okay. So now we can take a look at low temperature behavior of the fermion. So as you recall, so this is both Fermi distribution Q is given by for Fermi e to the epsilon tilde minus mu tilde over t tilde e to the plus 1 over 1 like this way. And when you take the t tilde goes to 0, what's going to happen? What's going to happen? So if this is a positive, this becomes infinity, so that will become 0. And then if this is the negative, this becomes negative, what's going to happen? It becomes 0, right?
Yes.
0. So therefore it becomes 1. Therefore this becomes here, mu tilde on next tilde. Okay, so that's okay. So if you plug this into the okay, if you plug this one into here, what you get is that the energy. So what you get is 1 is equal to pi over 4, and the integral is 3 over 3 over 2. So therefore, the chemical potential mu tilde is the temperature equal to 0 is equal to epsilon tilde f is equal to 6 over pi divided by 2 over 3 and 1.5. That's what we get. And so this is for Fermi energy. So therefore, if you look at the occasional number NQ, and then so this epsilon tilde and the mu this mu 0 sorry epsilon tilde f, what you get is like this thing. So the all state below this Fermi energy is the all occupied. Okay? And then after that you don't have any. So because of the Pauli exclusion principle, fermions cannot take the same state. So therefore, they take the occupy from low energy to the Fermi energy to get this. Okay. And then from here, we derive many things from many things. So we will derive low energy behavior. So for fermion, so we can just use this relation. And the low energy approximation would describe all those behavior around the low energy in next lecture. Okay. Let's stop here.
Yes,